Okay, now I think good morning once more. I think I want to believe everybody is available. You're able to see me, you're able to see the screen. Let me now try to make the screen full so that at least you are able to see me. You are able to see my screen. Now, okay, good morning once more. I can see we are now 135. I think now we can start. It's already 15 minutes past 11. We are a little bit late, but by the time we are starting, we are already around 10. So we are okay. Now, our in our last lesson, we talked about, we learned about the extraction of sodium and aluminum. Is that okay?
Yes.
Okay, good. And I want to believe that we are okay. So make sure that one of you remain unmuted, just in case there's somebody that need to be passed from where I am. Now, so today we are dealing with the extraction of copper, and I want to believe my screen is clear. You're able to see it. It is wide enough, and I think that's perfect. So in that kind of a scenario, we are looking at the extraction of copper. The rationale whereby we have looked at those methods is because they are likely going to be used. These are high chance. So make sure that you go through them well, you listen. If you're not able to get whatever we are saying, these topics are also being streamed. Mr. Obiro has recorded them. They are also, when you also go to my YouTube channel, you're also going to find the lesson there. So make sure that in case you miss, in case you are thrown out by the network, you are able to watch them later. And also for repeat purposes, good that you're able to review the lessons that they are being captured. Good, I think we are good to go. So then we're looking at the extraction of copper metal, and we look at, let's look at that kind of a scenario. So we look at the specific objectives. And the objectives of this particular lesson that now, by the end of the lesson, you should be able to name the ores of copper, describe the extraction of copper, the purification of copper, the uses of copper. You remember those things that I told you when you're extracting a metal, they are those things that you need to look at. Now, we start by looking at the ores of copper. And as you can be able to see, the main ores of copper, we have the copper parent, which is the chief ore. We have the copperite, which is copper 1 oxide. We have the chalcolite, and we have the malachite. Malachite is basic copper carbonate as captured there. This is not really the formula of the ore, but it's the formula of the main component of the ore. So that's the point that you need to understand that. Remember, the ore is not just this compound that we are saying here. It contains other impurities that are found there. So the most important thing for you to be able to understand is that the formula of the main component of the ore, whatever is being captured there. So we are okay there. We can proceed.
Yes, Molium.
And remember that it is important to understand how the exam is brought, by the way. Is that you're going to find that you may find somebody asking you, apart from the copper pyrite, name other 2 ores of copper. So make sure that at least you know at least 2 or 3 ores of copper is very, very much important for you to be able to understand. So we are okay, the ores of copper we have captured. So now, the first statement when you are dealing with the extraction is to know confirm the presence of the metal ion in the ore. You need to confirm the presence of the metal ion in the ore. How do you do that? You crush the ore into a fine powder. You crush the ore into a fine powder. Then you add, that is always the first thing Whatever you want to confirm the presence, let me just whatever you want to confirm presence of the metal cation in any rock, the first thing that you need to do is you crush the rock or the ore into a fine powder. Then you add that applies to all of them except sodium. So you crush the ore into a fine powder, add dilute nitric 5 to the crushed ore, then you fill. After filtering, this is copper. You add a portion of the filtrate to 2 molar ammonia. Formation of a blue precipitate, which dissolves in a to form a deep blue solution, confirm presence of iron. That is the best way to confirm presence of copper. Makio, just remember that what is the color of copper ions? What the color of copper? If we have a rock that contains, as if this is a rock that is containing copper. So what will be the color of this? You're given a rock.
Brown.
It can be which color?
Brown. Brown.
Copper exists in form of compound. Of course, it can be black if it's an oxide, or it's going to be blue or green. Let me just get you back. The ores of copper, anyway, we have one which is like red, like the copper 1 oxide is normally red. Copper oxide, copper 2 oxide normally black. But normally, if it is a compound of copper, the compounds of copper are either green or blue. Remember, you're not talking about copper metal. So the copper does not exist freely. So it cannot be brown. Brown is the copper metal, pure, when it's not mixed with anything. But when it is combined, it's going to be either green, like copper carbonate and copper chloride are green. If something like copper nitrate is going to be blue. Copper sulfate is blue. Are we getting the point?
Yes, yes.
Yeah. Just remember the copper salts are not just blue as you think, but it can be blue or it can be green. Now, to differentiate them, you see, green is also the color of iron. So to differentiate it, that's why you crush it. You add diluted acid to free the iron. You cannot test for cations when you're using a solid. You have to make them ion. You have to make them a solution. So that now the ions are free. Then from there now, you can now add the aqueous ammonia, whereby you're now going to get a blue precipitate, which is insoluble in excess. You can be able to get, okay. You can get a blue precipitate, which it dissolves in excess to form a deep blue solid. And I think you know what is this blue precipitate is copper hydroxide, which is blue. The deep blue solution is the tetrahamide copper 2 ion. Very much important. That's when you learn under ammonia. That's very much important. That's okay?
Yes.
So the key word there is you crush the ore. Number one, you add dilute nitric acid to the crushed ore. Filter. Those are key marking points. Then to a portion of the filtrate, add 2 molar aqueous ammonia. Formation of a blue precipitate, insoluble in excess, confirm presence of copper ion. Remember, even when you use sodium hydroxide, you're going to get a blue precipitate which is insoluble in excess. And you have those notes we gave you under the test for cations and anions. I think we can proceed. Okay, now we go to the concentration of the O. The concentration of the O, it improves the percentage of the copper, or rather of the O of copper in the O. So we are trying to concentrate it. We increase the percentage because the initial O contains a smaller percentage of the what? It contains a smaller percentage of the copper pyrite. So when you concentrate it, you try to remove impurities and increase the percentage of the copper pyrite in the O. Are we together?
Yes.
So the O is first crushed. Normally, the concentration of the O is done using a method called the froth flotation. We use a method called the froth flotation, whereby the crushed O is mixed with water and oil. Then air is blown through the mixture from below, resulting in formation of the froth. Are we together? That statement is very pregnant because you'll be asked, what is the method that is used to concentrate, or rather to purify copper pyrite? The method is, or rather the process is froth flotation. You'll be asked to name the raw materials for the froth flotation. And the raw materials are, we have what? We have the raw materials that we use in the froth flotation.
Water and oil.
We have water, we have oil, and we have what? Air.
Yeah.
Yes, that's it. Now, listen and listen very carefully. Because I want you to understand how to summarize the concept of metal. Any ore that contains sulfur is concentrated using froth flotation. So this will be the same method to concentrate what? To concentrate zinc and also lead, because you'll be able to see the ore of zinc is zinc bladed. It is the bladed, which is now the zinc sulfide. And for lead, it is galena, which is lead 2 sulfide. So any ore that contains sulfur, it can be concentrated or purified using the froth flotation. Are we in agreement?
Yes.
Are we okay? So this
Yes.
thing will also be used when you be purifying zinc and lead. And I will not repeat it. You better get that concept right. So what do? The Samanga, you crush the ore, then you concentrate it through froth flotation. So the froth flotation is whereby the crushed ore is mixed with water, oil, and then you blow in hot air. You blow in air. So let me explain the rationale using a diagram. And this one, remember, this kind of thing you're not likely going to get. You may not get this kind of a diagram anywhere. So this kind of diagram, you cannot going to be able to get it there. Look at that. So this now, you have added water. And you add fine oil. So what happens is the sulfide ore, they dissolve in oil. They dissolve in what?
Oh.
What is the sulfide? It is the ore of copper. The ore of copper is this one, the copper pyrite, which is CuFeS2. So this sulfur is the ore now dissolve. It dissolves in the copper pellet will now dissolve or rather get attracted or rather surrounded by the pine oil. The other impurities will now get dissolved in water. Of course, remember anything that is surrounded by oil is a little bit denser than water. So what will make it? We'll make sure that now the sulfide O will float because it's denser than air. Are you get the point that water? Are you get the point?
Yes.
Then the other components of the O will now settle at the bottom as gog. We can call it the gog or whatever, gauge, whatever, depending on where you have been harvested or presented, but we have the gog here, which now settled at the bottom. Then now, we now blow in compressed air. The compressed air now here will now, the compressed air now will form the sulfur to form a top layer here. This is what you call a froth. This is what you call a froth. Remember I said the sulfide ores will get surrounded by the oil. The oil will surround the sulfide ore, making it a little bit less denser. So when you blow in air, the air will force down the sulfide ores to be on the top of the what? To be on the top of this container. And you can be able to see if froth, it is now directed in a collectiva. Now we are going to have the froth is now collected on the side here. Are you get the point?
Yes, Mwalimu.
So, the only thing is that most of you, like in Alliance School, you normally don't go for, of course it's there. Now that you're having now the Mulolongo kind of survey. That Mulolongo kind of survey, wherever you arrive first, ule mtu anakuanga wa kwanza kama kumepigwa kiteli. What do you normally get? Unapata nini?
An oily top.
Unapata top layer, hiyo unaita oil top. Ndio tulikuwa tunaitanga top layer. Inakuwa na mafuta sana. So wherever you put some oil, any component of that contained oil will always be found on top. So this sulfide oil, the fine oil, the sulfide oil gets surrounded by the fine oil, but not any other impurities. So always will now be what? On top. And if you continue adding more water and we're adding more, remember the air inaenda mpaka chini. So it's being released from the bottom. So remember, air is a component of water. It occupies space. So it will be now be pushing now everything on top. And until it reaches now the top layer now, there is no more space. So now it's now directed to the collecting tank. And now the collected now froth will have a higher percentage of the ore. So if now whatever you put in this container was about 25% copper pellet, now whatever you're collecting on this point here will now be around, let me now change maybe here so that people can see. So whatever you're collecting here now will be containing around what? Maybe 70% copper pellet. Are you getting the point?
Yes.
So this kind of information is not captured in most of the books, but it's important that you understand the process of froth flotation. You crush the ore, then you add what? You add water, oil, then we have compressed air, which now forces leads to formation of the froth at the top, which is tapped and directed out and collected here. Now we have extracted, we have the ore and we have purified it. Now we now go to processing until now we get the pure copper, not copper pellet. Are we together?
Yes.
Now we go to what are the impurities And how are they removed? We have sulfur and other impurities such as arsenic compounds are removed as oxide in the roasting furnace. Iron 2 oxide is removed in the smelting furnace, whereby it reacts with silica to form slag. We are coming to that. So now these are the main impurities. If you're told like now, tell us now which impurities are found in copper pyrite. You tell us we have sulfur, we have arsenic compounds. We normally we have arsenic compound, we have iron 2 oxide, and all those kind of things. So these are how they are removed. We are coming now to the real process of extraction of copper metal. Are you ready now?
Yeah.
Yes.
Good. Now, the octopus technique, the process, this is now a specialized way of how the process of extraction of copper will look like.
Could you please go back to the previous slide?
Yeah? I go to the previous slide. Sorry. That one?
I think it's fine.
Okay. Perfect. Now, this is now the process of extraction of copper. So that you understand, first of all, by the end of the lesson, you need to know what happens in the roasting furnace. From the roasting furnace, we always go to the smelting furnace. What happens? I advise you to capture these things. Then you go and write it in your one ticket. One ticket to this one will require like 5 lines, and you are done with the extraction of copper. Just the way I've written it here. Then after we are through, you come back and tell us now what happened in the first roasting furnace is this equation. What happened in the smelting furnace? This is what happened. What happened in the roasting furnace? We have 2 equations. The converters, equation 1, equation 2. Then we obtain the blister copper. Then we go to purification by electrolysis. What do we use? What is the electrolyte? What is the cathode? What is the anode? And what are the 2 equations? You are done. But that is not what I'm telling you. I'm giving you the octopus map. By the end of the lesson, you should have this one in mind. Are you getting it, students?
Yes. Yes.
Yes, this is now a sketch map of how that extraction should look like. Very easy. Now let's now get now to the real extraction of copper using now that schematic diagram. Good. You have said the first statement, or rather the first thing in extraction of copper is what occurs in the roasting furnace. And in the roasting furnace, the copper pyrite is roasted in air to form copper 1 sulfide, iron 2 oxide, and sulfur 4 oxide. Remember I said, this is where now the copper, this one, as you can see, eka arrow ikienda hivi. This shows now the sulfur 4 oxide now is lost. We said, how do we remove sulfur impurities? Sulfur. Sulfur is, when you roast this one, it is escapes as a what? As sulfur 4 oxide. When now you form sulfur 4 oxide now on roasting, then the sulfur 4 oxide is lost, or rather is taken to the contact process to manufacture sulfuric 6 acid. Are you getting the point?
Yes.
Good, perfect. That's good. You're able to understand that kind of a thing. So that thing, measure that you know to balance that equation. Measure that you can balance that equation. Very important.
Excuse me, sir. Could you kindly pardon about the sulfur part?
Tunasema hivi, nikueleze na Kiswahili. Unaona hiyo copper pyrite iko na sulfur. Unaiona sulfur eh?
Yes.
Yes. Sasa iko na the copper pyrite iko na nini? Iko na copper, iko na iron, na iko na sulfur. These are, we only need, the only important product we need here is copper. We don't need sulfur. So the idea is, how do we remove the sulfur? That is part of the copper pyrite. So will you burn it first? When you burn this one, the products are what? Sorry. I think ni kama kuna mtu ana, it's like there's somebody with controls, eh? Somebody is having control over my screen. I think that is a Zenia witch. Now we continue. Nini inaendelea hapo, by the way? Let me do. Okay, good. Let me go back to this. And I think there's somebody who's there. Don't know how that one is happening without my power. But somebody has the power to control my screen. I don't know who is the host, by the way. I don't know whether I'm the host. Yeah, okay, good. I'm the host. Now, perfect. We continue. And we are looking at this thing here, that there is a student who had asked. There's a student who had asked how I repeat how to remove sulfur. And I said that the O is copper parent. The only thing that we need from the copper parent is copper. Are you agreed on first?
Yes.
Now, the others are impurities. They are unwanted. We don't need them. They have to be removed. So the first thing is sulfur. It's very easy to remove sulfur. You just burn it. Any component of sulfur in the copper parent will burn in presence of oxygen to form sulfur oxide. Sulfur oxide is a gas, so it is allowed to escape. Very easy.
Yes.
The iron 2 oxide is not a gas, so it cannot escape. So it remains. So after now the roasting furnace, we are going to have copper 1 sulfide and iron 2 oxide. And remember, these now two remains. They are not lost. Hizo mbili zinabaki. Tunaelewana?
Yes.
So now we have to remove, the next thing to remove is iron 2 oxide, which is removed in the smelting furnace. So from the roasting furnace, we go to the smelting furnace, whereby we have iron 2 oxide. You add silica to form iron 2 silicate. So now iron 2 oxide is now removed in the smelting furnace. So we are remaining with what now? Nini mebaki sasa? Copper?
Sulfide.
1 sulfide.
Copper 1 sulfide, which means we are not yet done with impurities. There are some components of sulfur that are still not eliminated. Are we together?
Yes.
So now we go to the next. So we now go to the second roasting furnace, which we also call the converters. In the second roasting furnace, we are also burning again. So we burn, and on burning, some of the, and the key word, you underline it, some copper 1 sulfide is converted to copper 1 oxide by heating it in a regulated supply of air. It is regulated. So not all copper 1 sulfide will burn. So we are going to have some of it in the first equation. That's why I told you in the converter there are two equations. So in the first equation, some of the copper 1 sulfide will react with oxygen to form copper 1 oxide plus sulfur oxide. Then at that point, the remaining, or rather the unreacted copper 1 sulfide, will now act as a reducing agent and now react with copper 1 oxide formed to form copper metal. There are two equations here. And by the way, everything is a solid here except for this one, copper 1 salt should be a solid, this one should be a solid, this one should be a solid, except this one should be a solid. This one should also be a solid. This one should be a solid. But the final copper should be a liquid. The final copper formed should be a liquid. Now, whatever we are going to get from this point is that, first of all, the first equation, some of the copper 1 sulfide, meaning all of it, will not react in bond in copper to form, bond in oxygen to form copper 1 oxide and sulfur oxide. The sulfur oxide now is lost. Then the remaining copper 1 sulfide react with the copper 1 oxide formed under what we call self-reduction process to form copper metal plus sulfur 4 oxide. This copper metal formed here is called the blister copper. Any question? Have you got it? I've said, remember where we started. First of all, we had the first roasting furnace. I can take you back. We had the first roasting furnace, whereby now the copper 1 sulfide, the copper pellet, burn in oxygen to form copper 1 sulfide plus iron 2 oxide plus sulfur 4 oxide. The sulfur 4 oxide escapes, rather is taken to the contact process to manufacture it sulfuric, etc. Now, after now, the sulfur 4 oxide is lost. We all remain with iron 2 oxide and copper 1 sulfide. Now, the iron 2 oxide is reacted with silica in the smelting furnace to form iron 2 silicate, which is removed as slag. So to metal sulfur oxide and to metal iron 2 oxide, we are all remaining with what?
Copper 1 sulfide.
So which now we take to the
second roasting.
Yeah, we take down to the second roasting furnace. And the second roasting furnace, the only thing that goes to the second roasting furnace is copper 1 sulfide, whereby in the first reaction, some of the copper 1 sulfide is converted to copper 1 oxide by heating it in a regulated supply of air, whereby the product is copper 1 oxide and sulfur oxide. Again, the sulfur oxide is escapes, or rather is directed to the fume chamber, to the collecting chamber. The remaining, or rather the unreacted copper 1 sulfide will now act as a reducing agent, whereby now it will react with copper 1 oxide to form copper metal and sulfur oxide. And this reaction is called self-reduction process. Then the copper obtained here is called blister copper. It's called blister copper because it appears as blisters due to escape of the copper 1 oxide. You see now when you have something like a liquid and a gas is coming out, then the copper will appear like now is a little bit distorted, will look like blisters because of the copper, of the sulfur oxide gas as it tries to escape out of the copper. That's why it appears as blisters, and that's how the name the blister copper came out. I think now that is clear about the two reaction at the second roasting furnace. That okay?
Yes.
Perfect. Okay. Now this one is, now we go. The copper obtained in this process is 97.5% pure, and it's called blister copper. It is blood, it is refined by electrolysis. We are saying the copper we obtain here is not pure. It is just 97.5%. And remember, these impurities will interfere with the electrical conductivity of the copper. So they have to be removed to make it a better conductor. So when you're electrolyzing, when you are now, this copper need to be refined because not pure. In the refinery, we use copper sulfate as electrolyte, pure copper as the cathode, and impure copper as the anode to obtain 99.8% pure copper. That's a direct statement, and you can now look at now the purification. So here we are purifying the copper. So in the purification of copper, we are using copper sulfate as electrolyte, pure copper as the cathode, impure copper as the anode. And then some of the impurities found in the blister copper are gold and silver, which now get deposited here as the sludge. In the anode, this one you cannot be able, you may not be able to understand much because you have not done electrochemistry, although there are some class that have done electrolysis of aqueous solution. These electrolysis of aqueous solution. These are a little bit advanced. You'll be taught much of this. But now here in the anode, the copper dissolves. This whereby we are going to have the copper rod, which was impure now, dissolving to form copper 2 ions plus 2 electrons. So this was impure copper. So it dissolves in the solution to form copper ions and 2 electrons. Now, the copper ions that are now in the solution at the cathode will gain electrons, forming copper metal. And that is how to make those kind of things. That's how you summarize the electrolysis. There are so many things that you can be asked. The examiner can tell you to write the equation of the cathode or the anode, and he has drawn for you the diagram. In many times, the examiner can also tell you to draw an experimental setup for the purification of copper. We need to know in that purification, what is the cathode? What is the cathode? The cathode is pure copper. What is the anode? Is impure copper. And now the electrolyte is aqueous solution of copper sulfate. And these are the equations that occur at both the cathode and the anode. Something might be a little bit tricky to most of you because you have not done electrochemistry, especially. I don't know how many classes have done the electrolysis of aqueous solution. That is a little bit, you'll be able to understand more on that, but you can be able to capture that. Make sure that you're able to know the cathode is made of what, the anode is made of what, and what is the electrolyte. Have you taken a screenshot on that?
Yes.
Yes.
Now, we continue, and now we go to the next slide. We go to uses of copper. This one, you just take a screenshot. There is nothing that I need to explain there. Just take a screenshot of the uses. You have taken a screenshot?
Yes.
These are just direct things. Nothing here to be tell you that. What is the now? Let me now take you now to the octopus observation model. This is the mother of all summaries. Are you ready?
Yeah.
Yes, for the octopus. Now, this is the octopus technique. The octopus technique, you're having the simplified diagram for the extraction of copper. So we start with the, so we have the ore is copper parent. Are you there?
Yes.
Tell me, what do you do after that? When you have the copper parent, what the first step? The first step is what?
Crush it.
You crush, and then you concentrate through what? It is crushed and then concentration by what?
Flotation.
Flotation, whereby we add air, water, and oil. Perfect. Then from there, we go to the roasting furnace, the roasting furnace. What happened in the roasting furnace? Who can remember?
Hot air gets in.
Impurities are removed, impurities such as sulfur oxide.
Yeah, so, yes.
Oxide.
So what reaction takes place there?
Copper pyrite is roasted in air to form copper 1 sulfide, iron 2 oxide, and sulfur 4 oxide gas.
Perfect. So we remember in the roasting furnace, we need hot air. So that hot air, we have the first equation. Look at it. Unaiona?
No.
Amuioni, I've done it in the screen. Ama, you're not seeing my screen.
It's only showing copper pyrite.
We can
I
see.
just show you. Yeah?
We can see.
Are you seeing my cursor?
We can see you.
Yes, teacher, we can see. We can see.
Okay, please.
We
Yeah,
can
I've just,
see.
I've just admitted this so that we go together, summarizing as the chairman of the Octopus. Remember, you are at the UPA Command Center, circling wisdom right from the deep sea. Now, we are looking at that point that we are the first roasting furnace. The equation that takes place is here. From there, now the sulfur oxide has escaped. We are now remaining one sulfide and iron 2 oxide. We go to the next step. Where do you go? Students, tumekuwa na nyinyi, tunaenda wapi kutoka hapo?
Smelting furnace.
So perfect. Whereby we add what?
Iron 2 oxide is removed as slag.
Is removed as slag mixed with.
We mix iron 2 oxide with silica, which we add silica, which now react with the you see, we adding silica, which will now react with iron 2 oxide, and you can see the reaction there. Everything perfect. Are we together?
Yes.
So now tunabaki na nini? What is remaining now?
Copper sulfide.
One sulfide, which now we take where? We take it to where? To where?
Second roasting furnace.
Second smelting furnace or converters.
Yeah, we take it to the converter, whereby we have, who can remember the two equations there?
Some copper 1 sulfate reacts with regulated supply of oxygen.
Yeah.
To
form what?
Copper 1 oxide and sulfur 4 oxide gas.
Some of the copper 1 sulfide, we got to go to the roasting furnace. Some of the copper 1 sulfide will now react with the, you can see, from here we are going to the converters, whereby now we are going to have some of the copper 1 sulfide react with the, react with oxygen to form copper 1 oxide and sulfur 4 oxide. The copper 1 oxide form react with copper, the remaining copper 1 sulfide to form copper and sulfur 4 oxide. Period. That's okay.
Yes.
Good. Then now we have blister copper, whereby now we now go to purification via electrolysis, whereby the cathode is pure copper, the anode is impure copper, and the electrolyte is copper sulfate to get 99.8% pure copper. And that is a summary of the entire process of electrolysis of copper in one page. That is make your work easy?
Yeah.
Pashika? Huh?
Yes, so much easier.
Yeah, that's a magnetic explanation using the Octopus technique. And you see, just one page, it is explaining everything. Cindy?
yes.
Good. Can we go to extraction of zinc? Assignment, a green rocky material. Kila mtu ama niwarudishe. Nyuma, have you taken a screenshot of that?
Yes.
Yes.
Remember, this flowchart will be available in school. I'll make sure that it's available when you get back. So we will hang it around in school. That it becomes, we can put it in the wall so that it becomes easy for students to follow. So that's it. Make sure that you are done with that. Let me now prepare the slide for. We can now go to the session of zinc. Please go to book 4, top-notch book 4, go to the Octopus and try to answer the questions of copper that are there. The last time copper was tested is long time ago. So please work on it. Now, can you go to extraction of zinc?
Yes.
Okay, good. Do moja. Summarize really bit. Good. We are now going to go into extraction of zinc. Okay, extraction of zinc. Okay. Just 1 minute. I'll be there. Tu moja tu ni. I want to make your work a little bit easy. Okay. Just hold on there. I'm just switching my slide. Just switch. Okay, good. Okay, now we are good to go. We can now be able to move. What are you seeing? Okay, you think? Okay, we are good to go?
Yes.
Okay. Now, now we go to the final extraction of zinc. Whatever I want is that I finish. I also give you an octopus for the other one, even for lead. That's not the bottom. So that becomes easy for you. Na mtu anapiga kelele hapo. So extraction of zinc checklist. Name the ores of zinc, describe the test for presence of zinc ions. The O, describe the concentration of the ore by the frost flotation, roasting. So here I am not going to repeat frost flotation because it's the same thing that we did. Roasting, convert the zinc to zinc blended to zinc oxide, reduction of zinc oxide to zinc in the blast furnace. Electrolytic extraction of zinc, uses of zinc and its alloys, and environmental effects of extraction of zinc. Name industry that should be located near the zinc extraction plant. Meona? Go sawa?
Yeah.
Okay, good. Now, the ores of zinc, the chief ores of zinc, we have the main ore is called the zinc blended, which is zinc oxide. And then we have the calamine, which is zinc carbonate. Are we together? So never say the ore of zinc is zinc sulfide. It is called zinc blended. Nalewana?
Yes.
Good. Confirm the presence of the zinc ions. None anaweza kumbuka how to test for zinc ions. These are things that they have done in school. Who can remember the qualitative analysis test for zinc? How do you test for zinc ions? What are the initial stages? That's what you have done. What are the initial stages someone to give us? Okay, don't tell us, don't tell me you don't know anything. I told you that we have an initial step that applies whatever you are testing for cations in. What is the first step? Are you there, Ama? Please say whatever you want to test for cation. We first of all crush the O into a fine powder. Then we add what? Are there people in class? So you don't remember anything that you said about the testing for cation. We take the oil is crushed and put in a beaker. Then you add diluted fiber acid, filter. The filtered, now you add aqueous ammonia. Drop it until in excess. Formation of a white precipitate, which is soluble in excess ammonia, confirm presence of zinc. There is no other cation that behaves like zinc. There is no other cation that will behave like this. It's only zinc. Are we together?
Yes.
I've said you crush the O. After crushing, you add dilute nitric 5 acid. Then you filter. This applies to all the oils except sodium. Make sure that is always the starting point. Crush the ore, add diluted 5 acid, filter.
Yes.
That will always be the first thing that you'll ever get. Filtrate, add aqueous ammonia to the solution, drop ice until the excess formation of a white precipitate that is soluble in excess confirmed presence of zinc ions. That's the only method that behave like that. That's different from aluminum. Then, remember, concentration of the ore by first flotation, I'm not repeating that. We already done it in our first lesson. It remains the same. We can continue, isn't it? Yeah.
Yes.
So this is the same thing. You remember? But the diagram is, this one I have tried to make it more magnetic. Maybe you can just take a screenshot. It's just the same. How to take the froth rich in the sulfide ore. Remember I said this one is for concentration of sulfide ores. Any ore with sulfur, it can be considered for flotation. Sawa?
Yes.
Good. Roasting furnace. Step 1. So the extraction is very easy. So the step 1 is that the ore is just thrown in a furnace supplied with air to form zinc oxide. So it's simply when you roast this one in presence of air to get zinc oxide and sulfur oxide. You remember this equation? Where did you see it? Do you remember this kind of equation in
manufacture of sulfuric 6 acid?
Exactly, whereby we can use metal sulfide as the starting materials. That's it. Because the idea is to get sulfur oxide. That's it. So if it is zinc carbonate, then you just again you heat carbonate to get zinc oxide plus carbon oxide. That's it. So the first thing is to convert the ore into an oxide by simply heating it in air. But sometimes the ore is contaminated with galena, which is now the zinc, the lead or lead sulfide, which again you also burn in air to form lead oxide plus sulfur oxide. There's no difference between those two equations. E na E. The only difference is this one is zinc sulfide, the other one is lead sulfide. And remember, the O for zinc, lead, is lead sulfide. So if we are also going through this, we are also kind of learning about extraction of lead, because it's still going to follow the same route. Even the concentration will also use the froth flotation. Are we together, students?
Yes.
Yes.
Then you go now to blast furnace. The ore is mixed with coke and limestone and put in a fire clay retort. So you'll also be asked what are the raw materials for the blast furnace in the extraction of zinc. Utasema, one of the raw materials is zinc ore, then coke and limestone. They are put in a fire clay retort. At the end of the retort is placed a fire clay condenser. Its mouth contains iron fluoride, which collects any zinc vapor and condenses it. Zinc oxide is reduced by coke to zinc vapor. So this is what happens now. The temperatures of the blast furnace are very high, above the melting point of zinc. So when you now get, these are simple equations now. You have zinc oxide and you have coke. Coke is carbon. So when you react carbon with zinc oxide, the carbon removes oxygen from zinc under reduction process. So you get zinc, but the zinc here you get it as zinc vapor, which is later condensed to form. You get zinc vapor and carbon 2 oxide. Then we have the carbon 2 oxide form further reduces the oxide that you can be able to see. It reduces the zinc oxide if there is remaining zinc oxide to form zinc vapor and carbon oxide. Those are the two reactions that takes place there. So we are already through with it. Hakuna kitu hapo. Step 1, concentrate. Step 2, confirm presence of zinc. Then you first of all roast the zinc sulfide to get zinc oxide. Then the zinc oxide is now reduced by carbon or carbon oxide to get zinc, which is now cooled. Yeah, Mr. Obiro, we can take Rocco. Amaili, you have already taken. Mr. Obiro.
Yes, sir. Thank you. Let's take a roll call, please.
Okay. There is a class called G there. I don't know what they are doing in this code. Three G and 3A. Where we have the serious jokers, but I think we are going to deal with them. G, the entire class, they have only 10 students out of 50. Kama jamaa wa kulala.
Thank you, sir. I think we are done. This 190 out of 197. Thank you.
Okay, thank you. Okay, we can continue. So we have said now in the blast furnace, after now we have the zinc oxide which has now been roasted at the first reaction. In presence of air, we now get zinc. So remember the first reaction is this, that the roasting furnace, whereby the oil is first of all roasted to get the corresponding oxide. Then the oxide can easily be reduced by carbon or carbon dioxide to form the corresponding metal. So that these metals are simply reduced or rather extracted through reduction process. Now in the reaction furnace, carbon react with the excess oxide to form carbon dioxide, limestone decomposes to form calcium oxide and carbon dioxide. So we are still explaining what happened in the blast furnace. So these are two, the calcium carbonate will decompose in presence of B to form calcium oxide and carbon dioxide. Let's look at the carbon dioxide now react with more carbon to form carbon dioxide, which is the main reducing agent. Zinc oxide and lead 2 oxide, which are reduced by both carbon and carbon dioxide to form zinc gas at the furnace temperature are above the boiling point of zinc. And that's the question that can also be taught to explain why the zinc is being collected as a gas, because the furnace temperatures are above the boiling point of zinc metal. We can continue. Now, blast furnace. Zinc vapor is mixed with lead spray. which contains the zinc vapor and prevents it from being reoxidized. Molten zinc separates and settles above the molten lead because it is less dense and is run off. Molten lead trickles down the bottom of the furnace where it is tapped off. So you need to understand these things. Whatever we get here is zinc vapor, but now it is mixed with lead spray, which contains the zinc vapor, and also prevents it from being reoxidized. Molten zinc separates and settles above the molten lead because it's less dense and run. So whatever I want students to understand is that the zinc blende is always mixed with lead, the galena, which is lead sulfide. So during extraction, they are normally extracted together. And when you get the zinc here, you get it in terms of zinc gas, or rather zinc vapor, which you need now to convert it to zinc liquid by spraying it with lead spray. Somebody will ask you, what is the purpose of adding the lead spray to condense the zinc vapor and also prevent it from being reoxidized? Blast furnace. The temperature in the furnace is 1000 degrees Celsius. Calcium oxide now from the decomposition of calcium carbonate combine with silica to form calcium silicate. The calcium silicate dissolves impurities to form slag. So zinc can also be extracted by electrolysis. So we are talking about here. Somebody asked you, what is the role of the limestone? You convert to form calcium oxide, which now combine with silica to form calcium silicate. And the calcium silicate now dissolves the impurities, other impurities found in the zinc to form the slag. Let's look at the summary on extraction of zinc. We have the main O, it's here. It is zinc blende, which is the main O. Then we also have calamine. Now, the main reactions are as follows. Remember, we have, first of all, remember the main reaction, we have the zinc sulfide being converted to zinc oxide. Then now, from there, we have the carbon. We have carbon here, the raw material, the blast furnace, which is it, limestone, carbon, and now the zinc oxide. First of all, you have to burn. You have to burn the zinc sulfide to convert to zinc oxide. Whatever you put in the blast furnace is not the zinc sulfide. We put the zinc oxide. So this carbon will react with oxygen to form carbon dioxide. The carbon dioxide react with more carbon to form carbon dioxide, which is the main reducing agent. So the zinc oxide will react with carbon to form zinc plus carbon dioxide. The zinc oxide can also be reduced by carbon dioxide to form zinc and carbon dioxide. Lead oxide can also be reduced by zinc to form, not by zinc, but by carbon to form lead. And lead oxide can also be reduced by carbon dioxide to form lead again, plus carbon dioxide plus carbon dioxide. Then we have on the composition of this, we have the calcium carbonate, which decompose to form calcium oxide. The calcium oxide combined with silica, which one of the impurities in the zinc to form calcium silicate. And you can be able to see now, now you get the zinc vapor, it is condensed, and when it is condensed now, we'll be able to get the two things here. That the molten lead at the bottom, and you're also going to have the molten zinc at the bottom is a little bit denser, like that. So here, this is now the lead spray. These are the condensers that are found there. Are we together?
Yes. Yes.
Yeah, so this summarizing those kind of things or rather the extraction of zinc. This will make your work a little bit easy. Let's now go to the final extraction. Okay. We also need now talk about that zinc can also be extracted using our electrolytic extraction of zinc. After roasting the ore to form zinc oxide, the oxide reacted with dilute sulfuric acid to form zinc sulfate solution. Any lead oxide from the galena react with acid to form the precipitate, which is insoluble lead-2 sulfate. You can be able to see from here. Then the soluble mixture of lead-2 sulfate and lead oxide is filtered of zinc sulfate solution is now electrolyzed, as can be shown in the next slide. So zinc can be extracted using two methods, either reduction or using electrolysis. So the anode is made of lead containing silver, while the cathode is made of aluminum sheets. Correct, this kind of information is wrongly captured in Kelby. They interchanged, but the anode is made up of silver and lead, while the cathode is made up of aluminum sheet. That's the correct scenario. The graphite is used as an electrolyte. Hydrogen gas could be evolved if you use graphite now. We normally, if you use electrons in terms of graphite, you get hydrogen gas. But now, because we are using zinc, we are using aluminum and lead and silver, then at the cathode, we get zinc is discharged from zinc solid. Then at the anode, hydroxide ions are oxidized to form water and oxygen to get oxygen gas. Again, this information is a little bit advanced because you have not done electrochemistry. So you'll be able to understand more when you'll be dealing with electrochemistry. But you can be told to draw the diagram. So now we go to after this, now we go to the summary of the extraction of zinc. And this one will just be just like the way we did for copper. Are you ready?
Yes.
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 Yeah.
So we have zinc blended. The first statement, we do what? What do we do? As usual, we do what?
Crush it
Crush.
into powder.
You crush. Then you convert it by flow flotation. What are the raw materials for the flow flotation? You require what?
Water and oil. Compressed air.
Good. Then you go to the roasting furnace. Roast furnace will require oxygen. Then you can be able to see from that point. So in the roasting furnace, so we are getting this. There's some that is missing here, but you need air here. You need air. You need air. And here we are still going to have the sulfur oxide escaping here. We're going to have the sulfur oxide escaping at that point. So we have in the blast furnace, we have whatever we have calcium carbonate, we have it now decomposing to form. Remember the roasting furnace, whatever happens there, we have the zinc sulfide and we have the lead sulfide burning to form zinc oxide and lead oxide. Then you go to the blast furnace, calcium oxide, calcium carbonate decompose to form calcium oxide plus carbon 4 oxide. Then we have the carbon 4 oxide react with carbon to form carbon oxide. Then we have now a reduction of the zinc oxide and the lead oxide there. So you can be able to see those kind of things. They're very, very much important for you to be able to understand. So we're having the reduction here. So the calcium oxide that is formed there react with silica to form calcium silicate. And the calcium silicate gets out a slag. Then now, this is now the extraction of zinc, whereby you crush it, concentrated by the flotation. Then you're going to have the roasting furnace here. We're having zinc sulfide plus or air getting zinc oxide plus sulfur oxide. The sulfur oxide escapes. Then now the remaining there, we said zinc is always mixed with lead. So we are going to have any of them, the two of them going to the blast furnace, whereby After now, we decompose the calcium oxide to get calcium carbon to get calcium oxide and carbon 4 oxide. We now have carbon 4 oxide plus carbon to get carbon 2 oxide. Then now we reduce the zinc and the iron, the zinc oxide and the lead 2 oxide to form the corresponding metals. Then now we have the extraction of zinc by electrolysis, whereby we have the zinc oxide react with sulfuric acid to form zinc sulfate. Then we also have, now we are going to have the anode is made up of silver and lead. The cathode is made of aluminum sheet, and the electrolyte is zinc sulfate. And then you get pure lead. We have the equation of the cathode. The cathode, we are going to have zinc ions gaining electron from zinc metal, and the cathode is the hydroxide ions forming 2 moles of water plus oxygen gas plus 4 electrons. Again, that summarizes the extraction of zinc just using 1 page. Are you getting it?
Yes.
Yeah.
You know, this summary, if you use this summary very well, it's going to assist you a lot. It's going to assist you a lot. Now, uses of zinc used in galvanization, whereby iron is coated with zinc. Remember, this question was even here, whereby you're even told what the importance of galvanization as opposed to painting. What is of galvanization as opposed to painting?
In painting, when the paint is scratched off the iron would rust, whereas in galvanization, even on scratching, it would not rust.
Yeah. And the negative terminal in red cells, making brass with copper, that is now, that's very much important for you to be able to understand. So then, pollution effects. And then when I'm dealing with, I want to tackle pollution effects for all the metals. Now, mosquito viduri, all the metals except aluminum, except sodium, they will lead to gullies. Which lead to environmental degradation will lead to land degradation, creation of gullies. These become water reservoirs for water, which becomes a breeding ground for mosquitoes. This become a breeding ground for mosquitoes. When now you create those big that are created as a result of the excavation, or rather the digging to get the metals. So all metals will lead to creation of gullies. Or extraction of metals will lead to noise pollution due to heavy machinery. Then all the sulfide ore that goes for extraction of lead, copper, and zinc. All of them have sulfur. So they will lead to what? They will lead to
Pollution.
pollution due to sulfur oxide. All of them, because they have sulfur. The pollution will lead to the sulfur oxide, leading to formation of acid rain. Carbon 4 oxide causes global warming, or metal that includes reduction, and that is for zinc and lead. Uliona zote ziko na carbon, because there will be release of carbon 4 oxide, which causes global warming. Even extraction of aluminum. Remember, the anode has to be replaced from time to time. Extraction of sodium, the pollution effect, we have chlorine gas, which is poisonous. Tunaelewana, eh?
Yes.
That's the, so mkumbuke, summarize tafadhali the pollution effect that are caused by the extraction of metals. Look at that assignment, you can try it. Look at more assignment look at more assignment in the extraction of in the Guru and book 4. And also, even if you have KLB, you have principles of chemistry, you can be able to get that. The students for 4C and 4R, remember what I told you. I want you to have, you must have done all the work on metals and electrochemistry. Let me see, let me give you another summary for maybe extraction of iron. Remember, by looking at extraction of zinc, we have already done it with the extraction of lead. Relevant,
Yeah.
Yeah, so this is a summary for the extraction of iron. Just take a screenshot. It may be useful for you because we don't have time. Extraction of iron. You have taken it?
Yes, yes.
That is extraction of sulfur, zinc. This is zinc is the same as for the neon, so that one we have done. So that's it. Extraction of lead, extraction of lead. Let me see. Lead and zinc are the same. So there's nothing that you need to have a look at that. So we have done for zinc, we have done for the blast panel, those kind of things. I think now we are good to go. We have done anything that can be done. Unless somebody has a question, make sure that you are able to get that. It's very much important for you to capture that. So any question? That's all for me. That's all for me, and I'm expecting any question. But just remember that now, make sure that when you look at your books, you're also going to find things like, you're also going to find, and make sure that for those who don't have that book, that's also an Octopus Flowchart, summarizing everything about organic chemistry. You can be able to use it for summary for that. So listen, students, I have not tackled issues of chemical property like now. What are the how does iron react? How does zinc react with chlorine? Those are things that you did in Form 1. Zinc plus hydrochloric acid, zinc chloride, plus chlorine gas, plus water, and all those kind of things. That's very much important for you to be able to understand. So anybody with a question? Anybody with a question, you can ask.
Cha, could you kindly put the slide on the pollution effects of the copper mining and stuff?
I done for zinc, but I can just do, we can just try to get, okay. Let me try to.
Thank you.
Are you seeing it, really? I'm trying to open it, please, just be patient.
Yes, yes.
I'm saying, just remember, both the O for copper is copper parent, which is Cu. The O for copper is copper parent, which is the as sulfur. The same for lead, the same for zinc. So all of them, they are going to lead to pollution by sulfur oxide, which forms acid rain. Number two, they'll also form, or extraction of metal lead to creation of gullies, will also lead to noise pollution due to heavy machinery. The other metal that require carbon, like the case of iron, extraction of zinc, and extraction of zinc, iron, and lead, carbon dioxide is involved. So in that kind of a scenario, the release of poisonous carbon dioxide and also release of carbon dioxide which form lead to global warming. Unaelewana, eh?
Yes.
So ukitaka vizuri, just group the metals. Like pollution by carbon dioxide, you can just these two, you can write these applied for iron, extraction of iron, zinc, and lead. For this one, that is now pollution by leading to sulfur oxide, applies for extraction of lead, also extraction of copper, and extraction of zinc. And I think that makes your work a little bit easy. Are we together?
Yes.
So unless somebody has another question, that's all from the UPA command center. See you when you open. I think this is the last lesson. Chemistry.
Very magnetic class.
Thank you, sir.
Na mtu anauliza raw material for the froth flotation. We have not frost, is froth flotation, which is now air, oil, and water. Goodbye. Enjoy your holiday.